Hello, and welcome to this presentation highlighting the importance of data-driven decision support and how Opus Suite can help you achieve this. My name is Ahmed Hatem, and I work as a product expert and customer success specialist at Systicon in Stockholm. Here at Systicon, we advocate the use of analytical lifecycle management at an early stage of a product's life cycle. This is often perceived as a challenging task. One reason for this is the limited access to mature data. The goal of this presentation is to convince you that you can make well-informed decisions at an early stage and that immature data must not be an impediment. First of all, I think we can all agree on the fact that the timing of the analysis is of utmost importance. If we want to impact the design of a new product or its support concept, we must also be prepared to deliver decision support at the right point in time. And that often means at an early stage of the life cycle. It's important to remember that the possibility to implement changes to the design without incurring high costs decreases with time. Since the supply of mature data is limited in the early phases, it's inevitable that we must rely on estimations of certain parameters. One such parameter, which tends to be quite difficult to get your hands on, is the failure rate. The accuracy of this parameter varies depending on the phase of the life cycle. At the beginning, you only have an idea of what the system could look like. You might have fancy computer renderings of the design, but those are not very useful for this purpose. On the other hand, you probably have a set of system-level requirements which you can translate into requirements on subsystems. But it's generally difficult to go further than that. In the next phase, the design of the system has matured, hence we have a clearer picture of the various subsystems and their components. At this stage, you can refer to reference systems, that is, similar systems which are already operational, to obtain an estimation of the failure rate. As we enter the production phase and start preparing for deployment, we can make use of data from suppliers such as FMECA. As we field more systems, we can start gathering numbers based on experience. Now, what can we say about the failure rate at these different stages? Naturally, one can expect the estimations from the early phases to be relatively uncertain. But the same can be said about the later stages. The failure rate you obtain from suppliers originate from test environments which don't necessarily represent the true operating conditions of your system. Even the accuracy of field data can be questioned. The outcome is influenced by factors such as infant mortality, especially for newly developed components. The failure rates depend on the condition in which the systems are operating, and after a while, one can expect the failure tendency to increase due to wear out. What I'm trying to say is that this parameter will never be accurate, so don't wait and hope for accurate data. But how important is it to have precise data? Well, that depends on what type of questions you would like to answer. The truth is that you don't really need accurate numbers for analysis you do in early phases. The reason for this is that at this stage, you're more interested in answering high-level questions, such as, should we design a subsystem with built-in redundancy? If so, how many levels of redundancy should we incorporate? Should we build the logistics support organization such that we have one central storage which supports our systems with spares and resources, but might be located further away from some system locations? Or should we go for a more decentralized approach with several regional stores located closer to the systems? What would be the benefits in terms of cost and availability if we opt for a module-based design instead of fully integrating subsystems into the platform? Again, what is more cost-effective? Regardless of what type of investigation you would like to do, the way to go about is the same. We start by modeling the different alternatives in Opus 10 and might end up with something that looks like this. Right away, we can see that Design alternative number 1 is more cost effective in the sense that we only need a fraction of the space required with alternative 2 to achieve the same level of availability. But it's not this simple, otherwise it would have been done at this point. Because of uncertainty, we cannot expect each line to be fixed. If we change one or several input parameters, the outcome will, of course, also change. The question is, will the effect of the uncertainty be enough to sway the results in favor of alternative number 2? To answer this question, we must repeat what we just did, but this time use a new set of failure rates and repeat this over and over again. But to have something to compare with, we start with a baseline for alternative 1 and alternative 2. In this case, we're lucky and obtain an outcome which, for both alternatives, is better than the baseline, but we might as well end up with something worse. As you can imagine, the outcome may differ by a lot from one replication to another. Certainly, 2 replications are not enough for us to be able to draw any meaningful conclusion. So let's turn up this number. If we run 500 replications for each alternative, we end up with this piece of art, where you can clearly distinguish the 2 alternatives. If we select the worst outcome of alternative number 1 and compare it to the best outcome of alternative number 2, the former remains the preferred option, at least from a cost-effectiveness perspective. Now, let's say that we select alternative number 1 and make an initial investment in spare parts based on that baseline model. What is the probability that we will underestimate the failure rates and therefore must make an additional investment in spares to compensate for this? This graph shows the additional investments as a function of the number of applications we run. As you can see, none of the 10 replications include an outcome where the failure rates increase to such an extent that we must compensate by acquiring more spare parts. As we run more applications, the results seem to stabilize around 5%. It turns out that in 90% of the 10,000 outcomes, you will not have to spend more than roughly 5% of the initial investment as an additional investment. This goes to show that the risk that you will make a wrong prediction and that you will have to pay a high price for that is not as big as you might imagine. Now, this is based on an uncertainty level of plus minus 20%. Let's experiment with this and see how larger uncertainty levels affect the final results. Again, with 20% uncertainty, we can expect around 5% in additional investment. For 30% uncertainty, it's just below 10%. For 40% uncertainty, we can reach almost 12%. Now keep in mind that we reach these numbers in only 10% of the outcomes, so chances are that you will have to spend less than this. So, what can we conclude from this? The value of producing results early outweighs the drawbacks of inaccuracies in the input data. The alternative would be to follow your gut feeling to make a guess or skip the analysis altogether. Both of these alternatives are, of course, unthinkable. Typically, at this stage, you would like to answer high-level questions related to system design or support system design. And for this, you must not have precise data. The results, as you saw, seem to be quite robust to changes in the input data, and even though we can expect the results to vary, the variation does not have to influence the final decision. And finally, people tend to associate Opus 10 with spare parts analysis, but it can be used for much more than that. I hope this presentation highlights this and encourages you to use it for more than just spare parts analysis. I hope this was an eye-opener for you and that I managed to convince you of the importance of early phase analysis and that Opus 10 is a great tool for doing this. Please don't hesitate to contact us if you would like to know more. Thanks for your attention.